I thought we have still time. Anyhow, couple of questions before I go to the new chapter, which is about the shaft design and the torsion, because there are some of the questions the gentleman back there asked that we want to address that. One question I would like you to go to your handout, the old handout, not the new handout, the old handout, and go to the page, please.
I threw it out. I thought we didn't need it.
What?
I threw it out. I thought we didn't need it.
You throw it out?
I just left it at my dorm.
Bad idea, my friend. You never throw out this. If I were you, I would keep it. You throw it out. Okay. That's the first one I heard. Okay. So you go to page, what page are we there? Page 11, please. Everybody just share it here. If you don't have it, share it with somebody. Otherwise, it has no effect for you. I don't have any extra either because I gave mine all away. So you have it there. Number one, I already covered in class with you. That is the change in the area. Yes or no? The second one is the change in the volume, which we covered that. So that's E. Remember the E factor, which was equal to epsilon x plus epsilon y and epsilon z. There is one homework I noticed. That's the reason I postponed your homework until next Tuesday, because there are several minor questions. Many of you can already answer that, but I needed some explanation there. Everybody understand what I'm talking about? The next one, in one of the questions, they are going to, it's like this is a plate like that. It is 8 feet here, 6 feet or 4 feet there, and then sometimes they ask you to calculate the change in that diagonal line from there to there. That is the one I haven't talked about it, but it is in your handout. Some of you already noticed, mentioned it to me. So the bottom of the page 11, it shows if it was a square plate means the angle is at 45 degree, which makes it the difference when you come to calculate the strain in that diagonal direction. I use the idea of a triangle. Everybody knows the triangle C square equal to A square plus B square. In this one, A and B are the same. So therefore, I took a 1 by 1, and I did that. Look at the epsilon at 45 degree. It become how much? It become 1/2 of epsilon x plus epsilon y. Everybody see what I'm talking about? So you can use that formula or this idea, whatever. So you can use that. But I remember your homework was not a square. It was rectangular shape. Yes or no? Go to the next page. That is the epsilon for a diagonal line if these two are not equal. So I choose one length equal to A, the other length equal to B, and I'm now look what is important here. This is not being discussed in any part of a book, but it is in your homework. You know what they expect from you? They expect you to do this by yourself as long as you understand the meaning of epsilon x and epsilon y. Everybody see that? That is the high expectation. I don't expect that anybody sitting here, not most of you, be able to do that. That's why I made it into handout. Everybody see that. But if you go there, you just look at the solution manual. This is the solution to the problem. It is not a subject being explained to you in the book, because that's high expectation. Is that understood? So therefore, I did it for you. So I took this one. It's a triangle. So I used the before the formation, after the formation, yes or no, right? Before the formation is A, so after the formation become A times 1 plus E epsilon x, and so on and so forth. And those are the formula. You can use this formula or you can use this procedure. Either way, it's not that big a deal. I'm not never asked that question in the quizzes and the final, so don't worry about it. This is for your information in future if you are interested to find. There are better method in future that you are going, but this is the idea that when you have epsilon x and you have epsilon y and you want another angle, it will be different. Is that correct? How much different? You can use this process. You don't have to worry about learning it and everything. Is that understood? It's just for your knowledge. Did you get it? Okay, so that will do it. The next question that I want to discuss, go to problem number 3, page 9, I believe. So let's see, one of the, no, the same one. There is a, oh, the other pages. Oh, I'm sorry. So that's this one, yeah. Problem number 3, what page is that? Page 9, I'm correct. So page number, this problem is exactly the previous. You see, I explained that briefly at the end of last lecture. I want to review it one more time because of the type of question that you are having. That it's very simple. Remember that what I did for you, it was like this. It was a 10-inch by 8-inch by a 2-inch thickness. Then I put here sigma x and sigma y. But it was free. Everybody should understand that. As long as it is free, every side is going to change. So we calculate delta x, delta y, delta thickness, delta change in volume, etc., etc. Now this problem is a little bit different, similar to some of your homework. So let's say that this is a plate with the same idea, 10-inch, 8-inch. E will be given to you. Let's say E is 10,000. KSI, let's say nu is equal to 0.3. That's beside the point because I'm not going to do the entire problem. I don't have time to do it, but I give you the idea. Is that correct or not? This time, this plate, the thickness T is equal to 2 inches. So the same idea here. But this side of the plate and that side of the plate is put between two rigid walls. So just like this. I'm holding it like that. Everybody, assuming my hand is rigid, would not let this expand in that direction. Is that correct or not? So this is the idea. Now this time, if you look at this problem, we have put this under a compressive stress of sigma x, and sigma x is given equal to minus 10 KSI, I believe. That's it. Is that correct or not? Yes? That's all. Then they ask you to calculate change in the length, change in the height, just to throw you off, change in the height, and change in the thickness. Is that correct or not? Yes? The same question as before, and change in the volume. Anything I can ask, that's beside the point. The major part of this problem, this has only one-dimensional stress. It looks like there is no sigma y, yes or no? And if it was free, that would be the case. If it was free, you only having one-dimensional stress, you can treat that like chapter 1. Is that correct? Delta equal to PL over E and et cetera, et cetera. Is that correct or not? Yeah? However, this is not one-dimensional stress because of this pressure, the plate wants to change in the y direction and you are preventing it from there. So therefore, there should be a sigma there. Yes, it's the form of compression. Everybody can feel that. Yes, it wants to go up. You have to push it back down. So you can use even superposition method. But I do not suggest superposition because superposition is long. I have given this problem exactly as a quiz, and some students did that. They remove this wall, they let it expand, then with the force they push it back. So that's the sigma. Is the force over area becomes sigma. But I'm showing you a better technique with the E. Is that understood? Yes? You can do that. But there is another one. We already know that the effect of this, we have to remove that, by the way. The effect of this and that is a sigma going this way. Is that correct or not? Yep. So that's the question we want this. So therefore, the question comes out. This is how you learn this one. Now, you go to the solution manual. You see this solution. You are preventing yourself from getting to that idea. This is what I don't like about what I was saying earlier. Is that understood what I'm saying? That by going to the solution manual, you deprive yourself from getting to this. You could do it. Is that correct? But thinking about it, one step at a time. Yes? And that is the process that I'm hoping that you guys follow and understand. So how do I calculate sigma y? I don't know what the value of sigma y is. However, I know that delta in the y direction, the same as epsilon in the y direction, must be equal to 0. There is no movement in the y direction. So why not use that as my formula? Yes. So as soon as I say that, then I go to the formula sheet, see what is the epsilon. Now, if you don't remember, that's no crime. I will give that to you. Is that understood then? So what's epsilon y? Now, everybody should know that. What's epsilon y there? It was sigma y over E plus, then minus nu sigma x, because this is the original sigma, and then minus nu sigma z over E. Is that in general? That's what I gave you. Is there a sigma z for this problem? No, sigma z is 0. Notice you only have sigma x and sigma y, so your conclusion is sigma z equal to 0 because there is nothing preventing there in the z direction. There is no wall here and there. Everybody, if there were another wall here, everybody on that, there would have been a sigma z here. Is that correct or not? Yes? Okay, so therefore, here there is no sigma z, not the equation. So epsilon y must be equal to 0. As soon as you say that, you have to think about it. Okay, if this is 0, E and E eliminate because it's equal to 0. You can multiply it by E. As you see here, sigma y become equal to nu times sigma x. Is that correct or not? Yes? What is the value of nu? 0.3. What's the sigma x? Now, here it is, 0.3 times what's sigma x? But sigma x is not 10 KSI. It is minus 10 KSI. Everybody understand that? So minus 10 KSI. So therefore, we have minus 3 KSI. So as soon as you put here a 3 KSI in the compressive format, isn't that the same problem as I did before? There's nothing different between this and the one I did last time, except the number changes. Yes or no? Correct? So can you calculate epsilon x now? Yes. Can you calculate delta? I don't have to do that because I just did that for you last week. I don't have that luxury to repeat that. Everybody understand what I'm saying there? This, after this part 1, which is the essential part of this problem. This is what I'm saying that some of you come to me and say, oh, I didn't get in your quizzes, and say, why didn't I get this and I didn't get that? Because the way I check that, I'm looking for the essential part of a problem. There is lots of math part of it, which I do not give that much credit, so if you make a mistake, you lose a point or two. Everybody the idea is important. We already solved the problem. Everybody see that? So after that, epsilon x equal to, you just put, but remember, anytime you put sigma x, this is sigma x, this is sigma y, sigma z is 0, you can calculate everything. Is that understood? Yes? Okay, you have another pipe, the gentleman back for that. So in the pipe, what was your conclusion? When it is on this part of it is under pressure. There is no sigma, let's assume this is y. There is no sigma y. Is there a sigma x? Is there a sigma z? So that's it. So that you go further like that. Now notice I have given the same problem at the quiz. On top of that, I put here a tension or can you do that? There is a sigma y as well. Everybody understands? So it becomes effectively 3D. Is that understood? Because the rod usually doesn't stay there. The rod is part of a machine part. Everybody under tension or today's lecture under torsion. We may do that too. Everybody. Then this part of it is under pressure. So you have all those stresses to add together. Is that correct? Yes? So you may have one-dimensional, two-dimensional, or three-minute scenario. We don't do 3D analysis in general, but we get this specific problem, which is all simpler. Is that understood? Yes? No. Now, the last two problems is number 93 and 98, which is about the stress concentration. That's the one. Everybody should have this table with you. So if you have your book, or look at it, because I don't have enough for everybody. If you have it, your book in your iPhone, or you have it there, look. If you don't have, you need a copy of that, and share it together, please. So in case so if I give one or two for each column. If you don't have, this is page 118 in the book. So 2-3 of you can share it. So here, two for your column. I don't know how much. If you have it in your phone or you have your book, just use it, please. That you can share. You can take a few here. See. Couple of them here, couple of them there. So here, you all have it. Okay, anybody else?
Where is that? Did you say in the book?
Page 118. Page 118. This is very simple. This is not the one. Page 118. That's the new material. I have 2-3 more. Anybody wants? Everybody has one? More or less? You don't want any? Okay. All right. Now let's look what happened. Here is the question of, we call it the stress concentration. But before we go through this table, this is not that important. This is again for your knowledge. I do not ask this question in the final or in the quizzes, so don't worry. But you have to be aware of that. This is a very important phenomenon there. It's been all explained in the book. You can take a look there, but this is what we do. Usually this is what you want to put in your note. Actually, this part of it is very important. Let's say that we have here a rod and we put it there. Technically, I always put here a load P at the centroid of the cross section. Yes or no? Correct? And then we said, lecture 1, sigma average was equal to force over the area. So when I cut it here, my internal force equal to the P, and that's what we end up mentioning to you. But this is theoretical. In actuality, if I put this P here at this point has an area equal to 0, yes or no? So force over 0 should be infinity. So under the load, I should get and stress, huge stress. Everybody understand that? And which is the fact. It will happen if I put my hand here. Look, if I put it here, look how stress is there, nothing around outside. Everybody understand what I'm saying there? However, this is sigma average. Sigma average equal to P over A, and therefore that's why we are assuming this is being uniformly, if I cut it here, this is P, that's what we mean. Uniformly being distributed everywhere. Is that correct or not? Yeah, that is what sigma average means. Is it happening here? Absolutely not. Because stress under this load become huge, and outside of that maybe become less and less. Therefore, one thing we do always, remember, we always put here assumably a plate there which is comparatively, it's rigid compared to the material, therefore it spread the force uniformly over the entire thing. So we have to do that, but in many picture we don't show that because this is assumed to be that way. Is that correct or not? So hoping that that become uniform distributed. In reality, that's not the case, because if this is, let's say, aluminum, and I put here a steel, which is a little bit tougher than that, it is still going to bend. Even if I put here a rigid plate here, that plate is going to slightly bend. As the result, the stress here most likely becomes something like that. Everybody understands? There is still more stress under the load than outside. Everybody see that, what I'm doing here. Everybody see what I'm talking about. There is a stress around that load. No. So therefore, in typical testing scenario, which you have to grab here, and pull this, you don't go to this here. So you go to 1/2 at the middle. So that you put 2 spots here. And if this is the L, we call this L, we call it gauge length. Gauge length is where the stress become uniformly distributed, because near the end you are grabbing there, so you have a stress concentration, so you have to get away from that point. Is that correct? So if the length of this, for example, is 40-inch long, so you only go to middle 20 and say, okay, the stress there is uniformly distributed. Above that, you have to make adjustment there. Everybody understand? That adjustment is going to be explained in each chapter. It's not important. It's not part of our analysis. You have to be aware there is a stress concentration here, a stress concentration here, so you should be able to remember some of your homework, they put 2 dots here and ask you to calculate the stresses between those 2 dots. Those 2 dots are the gauge length. Everybody, they call it gauge length. That's for your information. Some people ask me, so what is this gauge length? That's the gauge length. Getting away from the connection area there. This happens also if you cut material indifferently, a stress concentration happens there, which is the subject of that table I gave you. Let's look at this idea here. I'm going to be very brief because the idea is there. Let's say that you have here a blade. The height will be given. This height is D, for example. The thickness will be given to you. The thickness is T, and you are connecting this to another part here, for example, like that, like this. So 3D, you want to put it or that way. Is that understood? Yes? And then you put here a force P. Is that correct or not? Let's say that this is the D, and this one is a small d, according to what you have in your handout. So obviously, small d is larger than capital D, and if this item is going to break, it's going to break somewhere between B to C, so this length. So this is A, B, C. It's going to be BC, not AB, because BC has less height, yes or no? However, this is what we do. In other words, if I cut it here or cut it here or cut it here or cut it, it should be the same. But practice always show me the crack always start from corner. You have two pieces of wood, look at it. Furniture is connected there. The crack always is at the corner. What does it mean? There must be a stress concentration there. What we are talking about is this. So you want to put that in your note first. I don't know whether they show it in the table or not. If I cut it here, separate that, so we see this. So a little here. That's the middle part here. We are talking about sigma average. So sigma average is equal to force over area. So if you get that sigma should be, according to the theory, uniformly distributed from here to here where that connection was. Yes or no? Correct? But the actual scenario will be something like that at this corner, the stresses are much larger, and it goes at the middle like that. The sum is still the same, but the stresses here are much larger than sigma average. How much larger? In other words, I have to sigma actual. I have to multiply this sigma average. This is sigma average by a factor of k. That factor of k is larger than 1, correct? So in other words, I have to increase my stress calculation. So let's say you have there calculated based on the data that given, you have a stress average equal to 100. Because of a stress concentration, you have to take twice as much or 3 times as much. How much? You go to this table. Is that correct or not? Yes? Look at that table. So what you do first? First of all, this is what they are going to do, something I didn't show here. So first of all, this connection is the following. So you would do this and that one more time. This is the height, capital D. This is the height, small d. Then you have, we call it fillet. They are rounded it, because if they don't round it, this is disaster. Is that the K factor become much higher. Even if they do rounded it, which we call it the fillet there, so if you see all the equipment, it has round corner because of that. And the radius of that is R. It's given in the picture. You see that? Yes? That picture there. Everybody see D, R, and D. Is that correct or not? And it is under tension, for example. So all you have to do, calculate the value of the K. I don't have example, but I tell you this. Look at the data. You need first to calculate, look at it. If you calculate their R over small d. So you got R, let's say this R is ½ inch, this D is 2 inch or whatever, or 4 inch. You calculate R over D. As an example, let's say this R is very small. Let's say that end up to 0.12. No, numerically, you can get it from your picture. Yes? So you go to 0.12 there, then you go up. Now, what else do you need? There are 3, 4, or 5 curves there. Those curves depend on value of what? Capital D over small d. The next number you calculate, just follow what is there. Capital D, let's say that R. So let's say that the ratio, this is, let's say, 2 inch, and this is 3 inch. So the ratio is 1.5. Everybody understands? So it's happened that the D is 3 inch, and that's 2 inch. So the ratio becomes 1.5. So you have to go to curve of 1.5. Do you see that? So you go to 0.12 on the horizontal line. Then you go up until you hit the 1.5. Where is 1.5? Come on, go up. No, 1.5 on the curve. Look at the curve. The curve, D over D. There is a 2. There is the second one from 2 is 1.5. Yes or no? Right? Then what's the number? What do you read? 2.2. You see that? Everybody that did it? Go 0.12 on the horizontal line. Then go up until you hit the red line, which says 1.5. Everybody see that? And then read the K. What's the K value? This is simple graph. Everybody should be able to do it. What's the K value? 2.2. Is that correct or not? Yeah, approximate. This is very approximate. You a little bit up or a little bit doesn't. That means you have to add another 120%. So if you multiply this stress by 2.2, how much are you adding? You are adding 120% to the original stress. Everybody understand what I'm, because you are afraid of stress concentration. So this number always will be larger than 1. Is that correct or not? The K value changes depending on the way. The K value depends on the D and R. Everybody understand that, the way you build it. Yes? It's very simple. You can follow. As I said, many times I put that to the student. I said, read it, do it, because it's very simple. You have a question?
You said we're adding 120% what?
What?
You said we're adding 120%.
Because originally it's 100%, I'm multiplying by 2.2. What that mathematically, what does it mean?
Well, yeah.
If it is 100 and I multiply by 2.2, I'm adding 1.2 per 120% to it. Yes? That's the K value, yeah. If the K become 2, that means you are twice as much. That's what I said. Yes? All right? All right, that's no problem. Then let's yes. I don't want to, I say it as if I don't want to answer your question, but these are very simple scenario. What's the question?
That second one would be D, capital D over D?
Yes, look at the picture there. Here it says capital D over D.
Oh, okay, so not over R.
Did I put R there? Oh, I'm sorry. I say D, but I put here R. I'm sorry, maybe that was the confusion. This was, I said it D over D, but I for someone read it, write it out. So I'm sorry for that. It was D over D, whatever the curve said. Thank you. I said D over D, but I don't know why you write it R there. Yes? Correct? Because as I said, this is so simple, I don't want even to go spend time here. We have much more important discussion to follow. Is that another scenario is when you have a hole. When you have a hole in the material like this one, again the same thing happens. We know if this is in the tension, we have to subtract the hole. Is that correct or not? Yes? So again, this, if I make this, again, this is the P for your information. This is very simple. The P, usually we say sigma equal to P over the area. What area do I need? I don't need this area. I need area of the net area we have done in the past. We need this area. Is that correct or not? Yes? So in other words, you should understand that in this area, when I put it under tension, this is sigma average. The sigma average, again, is equal to force over the net area. Is that correct? We have done it in chapter 1. That's how we did it theoretically. Is this really practical? It's not, because that hole creates stress concentration around the hole. In other words, the stress is there. This is there by experiment. We are not proving it here. This is larger and there is star. Is that correct or not? So this is the black one. Sigma equal to force over the area as we were doing it. I have to adjust it with this purple one, so I should multiply it by another K factor. This one is very simple. We go to the right graph. So all we need is 2R over D. So this is what we have. This time is different. This time, this is the capital D. This is the R. R this time is the radius of the hole that you're creating this. And the balance of these two is D. So in other words, this is 1/2 of D and this is 1/2 of D. So D and D are different for this one. Look at this D and R and D are different from that D and R, and everybody see that. Because there are two different graphs, two different scenarios. If you have a hole, you have to again adjust that by a K value. K value comes from the right one. So all you need is a 2R over D. Is that correct or not? And then there is one curve here, so it is simple. Is that understood? Yes? You get the K value and put it there. All right. So those are the points that we want to follow. Now, this is what the question that I was raising at the beginning of the class, and I want you all guys pay attention to that. I can do two things here now for chapter 3. I can suddenly give you the formula and ask you to use it, which is the simplest way or fastest way for me to do it. But believe me, I have done that in the past, and that is the problem. When I give you the formula and I ask you how to use the formula, you probably will do lots of homework, but you don't have much insight if the problem becomes a little bit complicated and requires your thinking. Instead of that, I'm going to spend here about 10-15 minutes going to explain to you what's happening inside the shaft and how those stresses are going to develop there and what is the system. And that first 15 minutes, which many people would not pay attention to it, quite frankly. I have seen that in the past. Anytime I talk about that, they try to sort of doze off or just think about something else. As soon as I do the example, then everybody start writing it. It should be other way around. You pay attention to the first 15 minutes, all the homework become very easy for you to do. That's as simple as that, because you have to understand the technique and what is happening there. So please pay attention and write everything down. Although there is a handout there, I have given you a handout there, but be careful of the system and what we are going to happen in the shaft. First of all, we are going to go through a shaft. That means a rod like that. It's going to be round. So this chapter is all about circular system. We are not going to look at the other cross section. So it's not rectangular like what we had in the or T section and this and that. These are all about shaft. Shaft always are round, either solid or hollow. Now, what we do that is important. First, you have to understand a few things about the static, which people sometimes have a little problem with it, and now we are going to resolve that, or already been discussed in previous chapters. So if I have here a rod with the length of the L, circular cross section, and I applied here a torque, that torque, we call it, in this case, if this is x-axis, that torque becomes equal to mx. Everybody understand that? So one component of the moment becomes torque because of this. This is the shaft. We assume one side of it is fixed, which is not true usually. We assume that. And then we apply the torque here. Look first of all what happened. When I've applied here a torque, this end, look at this line, guys. You see this line there, purposely done this way. When I do that, look, that line turn around, yes? Is this elongation or is it angular change? So it is angular change. What should I expect here? Should I expect normal stress or should I expect shear stress? Because I have no elongation. Remember the difference between tau, between the gamma and the sigma? So here, because of this torsion, notice two surfaces here. One tries to stay back, the other one tries to rub on top of that. Everybody see that action create a forces between the two, which we'll show it in a minute, which should be in the intersection. So intersection means force over area, so become tau. Is that correct or not? Therefore, we should be looking for, look, previously this is what we did, guys. P, then we talk about sigma, yes or no? Then we talk, this is previous chapter. Look how similar the idea is. Then what was sigma? Sigma was stress. Then I talk about the epsilon. What's the epsilon? Epsilon was strain, yes or no? Then we talk about delta, yes or no? Delta was elongation. And then we talk about temperature, etc., etc. That things come later on. And then, of course, we talk about Poisson ratio, etc., etc. Is that correct or not? No, what are we talking about here? This is the idea here. This time I put it in color. So we should be looking for the following. The force actually is in the form of a moment, yes or no? We should be looking for tau. We should be looking for gamma. And we are looking for a deformation. Now look, you just told me the deformation is in the form of angular rotation, yes or no? Although it's very small, of course this was still, you don't see it. This, the way I do it, this is a very plastic, so you can see this is turning 10 degrees. But if it's still it's going to turning half a degree, yes or no? Therefore, we are going to look for, I'm looking for all of them. Phi. So suddenly delta becomes angular rotation, stress becomes tau, force, of course, the force becomes torque, and the strain becomes gamma, and all of this should be answered one after another one, yes or no? Yes? What's the question?
So if you were to twist it so much, wouldn't there be a change in length? Or are we not going to deal with that?
Which one?
If something like that were to be twisted so much, wouldn't it change the length as well?
It's this small, it's so small secondary that we are neglecting that. Yes, you see, if you don't maybe going a little bit back, no, that's the second. Like the other one, when it comes down, somebody asked me that question. If this is, look, this is the same question. If this comes down, notice you may be coming this way a little bit too. Because this, we always consider only the vertical, not like that, because that's too small to consider. Well, that theta was only 1 degree, remember, or half a degree, or this. So if the theta is small, that's a secondary. Yes? That's why, actually, if this is 30 degree, I cannot say this is equal to that. Everybody understand that? That's not the case. These are all for a small deformation. So we have very good question. That's what I call it important because everybody now have a feeling about what is happening there. Is that correct or not? Now, so now going there, now I need another relationship there. So the relationship there that we didn't put, so remember what was epsilon there? The epsilon was equal to sigma over modulus of, what was the gamma? See, this was their homework now. That's why I postponed your homework in order for you to get more involved with the tau and gamma. Phi is the fixture of this problem. Everybody understand? Your homework was all about tau and gamma. What is gamma equal to? Come on, guys, you knew that. Tau equal to tau over modulus of rigidity. These numbers all I need in order to go through this item. Now, the second item that I want you to understand is the static part. I hope you understand that part as well. So let me explain the static part here. Let's say I have here a shaft like that, and I put here T equal to 10 kips foot of moment. Watch out for the unit as well. That is just symbolic. Is that correct or not? What is internal? The internal, this is the external. When I cut it here, I want you to understand this part. This is very important. We have done it before. A student usually forget about that. So when I do that, let's assume this torque, which is external, is going counterclockwise. Yes or no? First of all, I have two torque here. This one should be equal and so this one should be going clockwise. This should be going counterclockwise. Now I'm going to change that from here to color. And you tell me why I changed that to color. Oops, so that should go that way. What does it mean that? We remember before we did the same thing. These internally, when I show it like that, that is static equivalent there. What is happening in the body is going to be stress. You follow what I'm saying that? I hope that you remember from the previous discussion. Again, I'm going back to show that because these are the most important part of your analysis that the student usually try to forget about that. We say P here, then I show you here N, yes or no? And N was equal to P. That's the static equivalent. But what is happening in this body right now? There is no, see, this is the point. Pull it. You see, physically, I'm pulling it. Physically, he's pulling it, yes? When I cut it here, is somebody sitting there and pulling it too? You and you guys are pulling it there. So what's inside this body? Sigma. Yes? This is what discussion we had before. You see, there seems to be losing it. What you have here is sigma, yes or no? That's very important for that. Otherwise, I cannot tell you what's going there. This sigma and this sigma are equal and now this sigma multiplied by area should be equal to P. Is that what we talk about? So inside the body is stress, but since this is difficult to show, then we show P, and here I call it. So because maybe I should show that in color as well. See, everybody see what I'm talking about? Yes? So this is the N, but this N doesn't exist there. That N is in the form of stress, and that stress is uniformly distributed over entire area. Then I say, therefore, if I sigma is a unit, like a pressure. That's why when I give you that pressure in the pipe, pressure is like sigma, yes or no? So when you take the pressure, you multiply that by area, that becomes your force. Actually, it's the other way around. Sigma times area becomes the force, then we calculate sigma to be force over area. Look how the different thing, everybody thinks of the sigma over this, but then they forget about that. Now I have to have, this is the point, write it down in your note. I have to have stress in this cross section. When I add it up, it becomes similar to a torque. Everybody understand? It must be going circularly. Everybody see that? This is the key for entire understanding of there. So the shear stress in the section is not going up and down. It must be in a circular format. Everybody understand? In order to become a torque, is that correct? Everybody knows the torque. The torque, you need a couple. Yes or no? We'll see that in a minute. That's one thing. The second thing is the static. Now we know that. So first of all, the internal, when I cut it here, I have the stresses. Those are stresses. Is that correct or not? How to come up, it will do it in a minute. Look how much information is here that you have to put 2 and 2 together. The second part is the static. Okay. Here I have 10 counterclockwise, 10, 10, 10. Action and reaction. Remember, the reaction become equal and opposite. On the other side, again, become action. So you have 2 free body diagram. Left-hand side and right-hand side, you can show either way. We talked about it before. Now, if I put this one here, I just want you to know, 20, or let's put it 30. 30 Kip's foot. And this is A, B, C. What's the internal torque there? We have done that. You should be very quick. I don't want even to discuss that. This you are the internal torque between B to C is how much? 40. Not 40, my friend. The internal torque between B to C is 10. That is something, if you make a mistake here this time in this kind of problem, I refer you to all the homework that we did in the past. This is repeat. The only thing is the vector force, you have it. Now you have the vector moment. What's the difference? To me, it should not make any difference. What do you see there, guys? 10, yes or no? What do you see here? 40. That's the 40 is in this side. So you're adding up together. Is that correct? Or I believe you knew that, but you just overlooked it. Is that correct? Whoever said 40 there. Is that yeah, I'll forgive you. All right. All right. Now, if I do this, this is a static by Kip foot. Then what happened? Here is how much? Here is still is 10. On that AB will be 20, but it's opposite side. So in other words, now we are talking about the phi now. We are talking about the phi now. If I'm looking at the phi, which is the angular rotation, this part is going to rotate counterclockwise with this value. Yes, that's it. We get the formula for it. And this part is going to go like delta. Delta sometimes was positive, sometimes delta was. Here the phi sometimes is going this way, sometimes is going that way. Depends what kind of a static scenario you have. That you cannot miss for any part because these are repeat. Is that correct? So you give you a shaft. There are 2, 3 torque on it. So you have to add or you have to subtract. Then you calculate the phi, which is the angular rotation. Is that correct or not? All of that being excellent. Now let's get to the formula. Before I get to the formula, I need to ask you a couple of other questions or maybe leave it for later on. So there are some more questions about the area. Everybody knows what the area is. About the first moment of the area and the second moment of area, which is the moment of inertia. Next 2 chapters is all about moment of inertia. You need to review that when we get that. Let's see that. Yes.
Is there a sign convention for the twist? Or
yes. Every time you go clockwise, we are going to call it negative rotation. Write it down. Like we go with the moment, the sign of the moment. Anytime the rotation is counterclockwise, we call it positive. So good question. Well, I was going to mention that, but yes, here the phi is going like before. Counterclockwise is positive, clockwise is negative. Exactly like the moment. We treat that always. Okay?
It's just because the moment, I just pick the sign, so that's why.
I'll tell you what you may have done mistake. You either can consider the we'll talk about it when we get a little bit better at that. I know. You have to go action, 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 or reaction, reaction. You cannot jump from action to the reaction, then it changes, direction changes.
I'll just keep it like this.
Yeah, just look at like that. I'm going to explain all of that. I know where the controversy comes. I will explain it when we do the homework, and I will explain all of that. Don't worry about it. That's the key issue that people make mistake. You are half of people make that mistake. Don't worry. I'm going to make that very clear. Let's go step by step, slowly now. Now, here is the next 10 minutes, so you have two ways to do it. You can close your eye and go to sleep if you want, quite frankly. And when I get to those 2 formulas, I give it to you, use it, or pay total attention. It's your choice, because it is sometimes people go to sleep because it's all math, a little bit math. It is all in your handout. But nevertheless, it gives you lots of information. So now, here is the scenario. I have to have, by the way, I have to do one more static there. If you have the rod like that, right now, this is the x, yes? This moment, which is mx, become torque, yes or no? The other two m become mz, look at my thumb. This is mx, look at it, like that, yes? This become torque, this become bending, which is, look at my thumb, mz, and this one become my. So we have two bending and one rotation. But this exchangeable. If I hold the rod like that, this is the y direction. Now which one is torque? My is torque. The other two is bending. So this is exchangeable. But for the discussion, we always put the shaft here in the x direction. So don't assume mx always is the torque. One of the three components of the moment become torque. We discussed that before in the lecture 1. And the other two become bending. Which one depends how you put your shaft in the system. Is that correct or not? So that is the idea of a static again. Now, to go any further, I'm going to make a cut here, and I'm going to show this larger, which is in your handout as well, in the area there. So if this is the cross section, and of course, this should be a complete circle, which is sometimes difficult to draw. Anyhow, so this is it. Now, we are at this point here. I'm going to put here a dA here, or delta A, or dA, or delta A. Better put a delta A, because, yeah, delta A at a distance of rho. So we are not on the outside of the shaft. The radius of the shaft in this chapter, we don't call it R. For whatever reason, we are going to call it C. So the radius of the shaft is called C. And a distance from the center of the shaft, which is O, is called rho. So rho changes between 0 to C. So our variable will be rho. And since it is a circle, therefore it is circular. So if I have a dA here, similarly, I must have a dA there, which has the forces in it. Remember, those rubbing forces are in the section, yes? So let's call that one a force here. This is the one that gives me the stress. So I put it in the column. So it's going to be tangent to this circle here. There is a circle here. So this is dF. It's not perpendicular to the section. It is parallel section because of that rubbing action. Everybody see what I'm talking about? So this F, obviously, these two F, because they are at the same distance row, these two F must be equal, and so the sum of the F must be equal to 0. So there is no F here. As you see there is no F here. So if I'm looking here, previously I had an F here in chapter 1. So my sigma was parallel to the F. Everybody understand what I'm saying? That here, I don't have any F. As you see, this dF and this dF cancel. If I take two similar again, here and here, here and there, here, every two point here give me dF equal and opposite. So sum of dF is equal to 0. However, I can write the following formula. These are the formula that I'm going to put here. I put up here. Tau at that point is equal to dF force over area. Yes or no? By definition. Force is in the section. dA is the area. By definition of the tau, tau is equal to force over area. And it is at a distance rho, so we want to calculate that now. We want to know, first of all, it looks like it's going like that. Is that correct? So it is in circular shape. It is not vertical or, remember chapter 1, we had the shear too. Remember in chapter 1, we had the shear. The shear was like that, going up and down. These shears are not totally different. Everybody see the totally, because the circle is rubbing like that, so it is circular shape. Everybody see that according to what we have here. So this tau, so first of all, we can rewrite this in this format because I need a force too. dF equal to tau dA, so either way is correct. So that's the equation. Now, sum of dF, you agreed on over the whole area, must be equal to 0 because the F and F cancel. Is that correct or not? Yes, for every two. However, is this a couple? Everybody see that? Does this create a little torque here? Forget about this one. Look, dF times rho become, I'm going to show it in a little color here. So I'm going to show it here too. See, here is my external torque, yes or no? Here is my I put internal in blue. Everybody understand that? This is not the valid one. The valid one are the stresses, yes? Look, this times that gives me this. Is that correct or not? Everybody see what I'm talking about? Look at dF times rho, looking like a couple. Give me a little stress here, yes or no? But this one does not cancel that. That one also add to it. Everybody understand that? So if I get all the dF and multiplied all the dF by rho, that becomes little torque here, yes? I do this, I do this, I do that, I do that, I do that. So if I integrate that all over the area, what should I get? This blue one, is that correct? But these are stresses in the format that it gives me the torque. Is that understood? So the net result is a torque, so we show it in the static format. Is that correct or not? So again, like last time, this is the real torque applied. These are stresses. That's what we have internally. There are stresses. The stresses are in this format. Very important thing. It has to go like that. So around this circle, they are all the same, yes or no, because it's symmetrical. Now, the only question is, what is at the point, this point? At this point, rho become equal to 0. So that point, the center of the circle, doesn't have any stress, yes or no? And as we going outside, maybe the stress keep increasing because the rho keep until outside, write it down, and on the outside, the tau is maximum. This is the most important part of your analysis. On the tau outside, because become delta F times rho, at the center, rho is 0, and when we go up and up and up, the rho keep increasing, the tau keep increasing, so that this is rho times dF, this becomes delta T, but then you integrate that over the whole area, it must be equal to T. Is that correct? This is the most important equation. So for this chapter. And the format of it, as I said, this will help you later on not to forget. People come to ME 219, I ask them to do the shaft design. They don't know. They know formula. I give you the formula in a minute, in 5 minutes. But they've known the formula, but I ask them, where is the stresses? Show me the stresses. How these stresses change? They have no clue. Now you have. Of hope you don't forget that. Put everything in boxes and remember that. The stress at the center, one more time, is 0. Stress is in circular format, and as we're going up, the circle is linearly changing, and the maximum is on the outside. Very good. Now let's get to the next 4 or 5 minutes, which really puts you in. What's the question?
Oh, it's just the stress in the middle is 0 because it's actually loaded. If it were loaded.
No, that doesn't matter because the stress does 0 because it doesn't turn. You see, it doesn't turn. Because we'll get the formula in a minute. You will see that. So because here, when you turn it around, the outside will shift, but the center stays at the center. Look, this line, the more outside you go, the more rotation you have. So therefore, that is the case. All right. So having this formula now set here and this one, now we go to the next part of it, which I'm going to go a little bit quicker because otherwise I cannot finish there. So this is the whole scenario again, one more time. The way I draw my equation now is based on the understanding here. Everybody understand that? Then this is what I do. I get a length of L, then I take a core here. The core is that core that I was talking about. This distance from here to here is rho. That distance is C. So it is in your handout. If you don't want to write it down, that's okay too. So therefore, then I'm going to take this core out, this middle part. This is the core inside. So I'm going to show it here. This is the middle part of it. So let's maybe put it in color if you want to. This part, which is the core part, I'm going to put that one here. And then I draw a line here. Now here, notice at the end we have a circle here. Now this is what happened there. Let's say this is point A, this is point A. The analysis is this, that I applied here a torque, yes or no? When I do that torque, this line, as you just showed you a little while ago, this is in the exaggeration. A goes to A prime. Look, one more time. This is what I'm talking about. Look, guys, let's assume this is that core, okay? Yes? This is that line, right? When I do that, look what happened there. Look, this point, when I torque it, this point is here, comes a little bit down. Yes or no? And this line goes a little bit down as well. This, which we show it here, so this is the center O. that point O go to A prime. This is the phi, because that is at the end, this is the relative angular rotation. Everybody says this is 0 and this is moving. Is that correct? So that's the phi. So we want to look at the phi. Phi is there. I don't. And this is, by the way, gamma. You don't have to worry about it because that's the change, and this is the length. So that's the change in length over delta over L. That's the gamma. Anyhow, so I assume that one. All you have to do, use a little bit geometry quickly. In this triangle, I can write tangent gamma equal to gamma equal to. The reason I'm doing that, because there is some understanding in between. You may or may not want to remember all of this, except that one is important. This is not as important, but it gives you also more information. So gamma become equal to AA prime divided by L in that triangle. Tangent gamma equal to AA prime divided by the length of the shaft, which is L. In this one, the diameter is the rho because we are in the core. Here we are in the core. So tangent of phi equal to phi equal to AA prime over rho. Notice AA prime is the same. This length should be equal to that length. So you have to make these two quantity equal, yes or no? So from here, you get gamma L equal to phi times rho from this one. Then you get gamma equal to phi times rho over L. That's what I was talking about, guys. Look what happened here. Phi usually is constant, L is constant. So gamma changes with the, this is confirmation of what you were just saying. When rho equal to 0, where are we? Right down in front of this equation. When rho equal to 0, where are we? We are at the center. Gamma is 0. If gamma is 0, look at this. If gamma is 0, tau is 0. Is that correct? No strain, no stress. That's exactly what you were asking. Is that correct? Or now come by equation. Yes? When rho is equal, no gamma, no strain, no stress. Correct? When rho becomes C, that's the highest value. Again, and it is linear. Everything we said that is here because rho is linear. Yes or no? It's a line. So therefore, gamma max. Where is gamma max? Gamma max is where we are on the outside of the shaft. Then rho must be equal to C. Is that correct or not? So put rho equal to C. C is outside when this gets to that point. Is that correct or not? Therefore, gamma max becomes phi times C over L. And the next thing we want to do, we want to divide these two equations by each other. So gamma over gamma max. So here we go. We are done with the formula. Just give me one more minute. We are done. So here we go. So divide this equation by this equation. So gamma over gamma max become equal to phi, and phi eliminate L and L over. So become rho over C, or gamma one more time equal to gamma max, rho over C. Again, one more time, confirmation. At rho equal to 0, gamma is 0. At rho equal to C, gamma is gamma max. The same thing again and again. Now this time, because I want to get to the tau, all I need to do, I have to multiply gamma by G to get into my tau. Everybody understand that? So what I did, I multiplied this side of 2 by G. So this is tau. And this one is tau max. Is that correct or not? Rho over C. Is that correct or not? Yes? Okay. Rho over C. So tau. This is tau. This is tau max. Is that correct or not? Yep. Yes? According to that formula there. Gamma equal to tau over G. Tau equal to gamma G. You already have your homework, etc. Now plug this one into that more important equation, which was this one. T equal to integral over area of the tau, which is tau max, rho over C, multiplied again by rho, yes? Oh, I'm sorry, this one, I have to change it to that. So this one, I have to tau dA, because dF is equal to tau dA, so I forgot about it. That's the same thing. Is that correct or not? Yep. dF, so I have to put tau there, I did it. Then I have tau, dA, and rho. Is that correct or not? Yes? So I have to multiply it by rho, and I have to multiply it by dA. Is that correct or not? Then you will see here what happened. Tau max is constant, it comes out. C comes out, then we get integral of rho squared dA over the area. What's the integral of rho squared dA? Come on, guys. What's the integral of rho squared dA? Have you seen something similar to that? Have you seen integral of x squared dA, y squared dA, rho squared dA? That's the problem, again. The major problem is you go through the static, you go through chapter 5 and chapter 8 or 9. One was centroid, the other one was moment of inertia. You remember the process, but you don't remember the concept. Okay, I am going to show you that concept. It takes me 2 more minutes, but I have to do it. Because I need it for this chapter, I needed the chapter. I'm going to summarize chapter 5 of your static and chapter 9 of your static. One is centroid, the other one is the moment of inertia. In one paragraph, one sentence, one picture shows you the whole scenario. This is it. Anybody remember this picture, understand this meaning. This was polar moment of inertia. Nobody remembers that because nobody remembers the concept. Everybody knows how to calculate x bar and x bar, that table that you were writing, that what is on top of the table, that's the question. Nobody pay attention to that. So I'm going to give you this. So please write it down in a separate page and keep it for next chapter and next chapter, because we need this one for chapter 4. We need this one for chapter 6 as well. Everybody understand? We need the Q, we need the I, we need everything that you learn in static, we learn. This is the idea, guys. We have three quantity here, one another after another one, all related, as simple as this. You have here a dA, yes or no? Correct? Everybody knows dA because everybody knows if there is a curve here and you want to calculate the area, I don't need this anymore. I need to calculate area here. You say area is integral of dA over the area, yes or no? Correct? You have no problem with that one, yes? But you do have problem with the numerator of the x bar and y bar, because you learn the process, you do not remember the concept. You need to calculate the Q. Q was what? Was the first moment of that area with respect to x-axis, and anytime you write in your table AI, YI, that is the Q. Everybody understand that? I don't know whether you learn it that way or not, but the numerator of x bar and numerator of y bar are the moment of the area about the x-axis or about the y. You get the area multiplied by y, yes or no? Exactly what I'm going to do. This is the area multiplied by y, yes or no? That is the Q about the x-axis. Everybody understand that? So therefore, the Q about the x-axis is equal to dA times y, yes or no? The same formula. Is that correct or not? However, if this belongs to a larger area, I have to integrate that, yes or no? So the integral of that one over the area, we call it first moment of area with respect to x-axis. You have done it many times without understanding it. This is 4. This is 2. This distance is 5. You said 4 times 2, 8 times 5. Yes or no? Yes, that's what you are doing. Is that understood? Area times distance y become qx, or the first moment about the x-axis. If this is integral format, you do it this way. If you use composite section, it's the same thing. All I did, I changed that to dA. Everybody understand what dA times y. Is that simple enough? Yes? So do we have a Q about the y-axis? dA, see, now you are writing it yourself. dA times x, yes or no? Correct? If you are listening, of course. I have to rub it in. Is that x? Is that correct or not? Yes? And that becomes Q with respect to y, which we needed for chapter 6. We have to calculate the Q of an area. Q of area is area times y or area times x. You have done it many times. Is that correct or not? Yes? That is the meaning that you are using. In integration, you use it like that. In composite section, this becomes a 3 by 2 inch. Is that correct or not? Yep. Then we have the moment of inertia about the x and moment of inertia about the y, which is the not first moment. It is the second. See, everybody remember that. So I have to take one more moment. I have to add one more y. Yes or no? So if I take this one and take the second moment, get this quantity multiplied by y, so it becomes y squared dA. I'm home free. That's the definition of Ix. Y squared dA is Ix. X squared dA, of course, will be Iy. So we have one, we have here. Of course, the one that you didn't answer is dA times rho squared, which is polar moment of inertia. Yes or no? dA times rho again. Is that correct or not? Then that's exactly what we have there, guys. This one, write it down, is polar moment inertia of a circle with respect to the system. Anyhow, that finished the problem. Let me put all the numbers together, so we need to put it here. So I'm going to erase that, and now we end up with our first formula here for this chapter. Now, torque will be given to you. Dimension will be given you. Now we calculate the tau. Look at that equation. What happened? At that equation, after you do that, tau max become equal to tau max. Where is tau max, by the way? Tau max is on the outside. Look at that. Tau max equal to, look, T times C divided by J. Is that correct or not? Look at that. It's all there. Tau max equal to T. This become equal to 2. Remember, T times C divided by J. Is that correct? So that's your stress. Tau max equal to TC over J, which is where? It is on the outside. So now here is the formula. I have here a torque. I have here tau, circular shape. Is that correct? That's the tau max. Yes or no? Correct? Now, if you are here, that's not the tau max. You have to change C to rho. Everybody understand that? So for any other inside, this is for outside. For inside, tau equal to T rho over. Of course, this becomes plus or minus because it may go in this way, it may go into the other way. We talk about it later on, about the sign of it. Is that correct or not? Yes? All right. And then one more formula I need. This is my stress. Now, stress, you see, we went from here to here. Here we go. Now I want to calculate the phi. What's the phi? Phi is the angular deformity. All I have to do in this equation, there is a phi there. You see, I can calculate here gamma max from here. This equation, you subtract, put it here again, put here G and G. You don't have to do it because it is your handout. Then you calculate the phi. This one, G gamma max, become tau max. Tau max, it is already TC over J. I can do it here. TC over J. I want it equal to G phi C over L. C and C drops out. Phi become equal to TL over GJ. Everybody said that. You don't have to prove that. It is there in your handout. So phi, which is the log delta, become TL over G. Exactly like delta. Look how similar that is to delta. Is that correct or not? Delta was PL over EA. Now everything changes to a different format. Is phi depends on the value of the torque. Look, guys. The more torque I put, the more phi I have. Yes? Depends on the value of L. The more L I have, the more phi I have. Everything is there like before. What is the G? D is the modulus of? This is still, two of us cannot rotate it that much. Everybody understand what I'm saying that? So it will be in the denominator. Of course, the cross-section. Not in the form of A, in the form of the moment of inertia. The more area you have, the more moment inertia. So it is difficult to twist it. All is there. So the entire chapter is about this. Write it down. These are the stresses. Stress either outside or inside. We gave it out, which is the sigma. And this is the formation, delta. And the easy part is this. The rest of this chapter, I don't have even to explain it to you. Everything is exactly the same as chapter 1 and chapter 2. You can do the determinate problem. You can do indeterminate problem. You can do all of that. But it's going to work like that? Absolutely not. So today, the rest of the time, I don't know how much time do I have?
4 minutes.
4 minutes. That's good. Because I can give you the essential part of the idea there. Then we are going to entire Tuesday. We're going to have example maybe Thursday as well. The only thing that extra in this chapter, besides what we learned in chapter 1 and 2, quite frankly, everybody should be okay with this chapter except the gear system. Remember, the shaft have a gear, like your car. What happens if I put a gear? Of course, everybody knows that I have to increase the speed or decrease the speed or increase the power. That is something new in this chapter. Everything else after you change the delta to phi, and you change the sigma to tau. Everybody understand? And the format is there. Now, in order for you to understand what we are going to talk about, I'm going to do example number 1, an essential part of it, and continue with it. Now, because some of you may want to go a little bit forward, get ahead of time. Go to the first example given there. Go back. Forget about this. So I'm going to discuss that. No, go further. This one, page 5. Page 5. Because this is important. In order not to forget what we just did, I need to at least to show you one example. And it is so simple, you will be surprised at how much knowledge you already have extra. You are not like 3 weeks or 4 weeks ago. And here is the shaft there, guys. Here is the shaft there, sitting here. Okay. We assume one side is fixed, which is not. Usually it's a bearing, but we are going to assume that. And then here I have, I believe, there is a 800 pound-inch or pound-foot, pound-inch of torque going clockwise here at point A. Then at point B, everything will be given here. This is just for the next 4 minutes in order for you not to lose the idea there. So at point B, we have to put a torque there going in the opposite direction. 2,400 pound-inch. Is that correct or not? Yes? No, I know that. I remember that. I just did it 10 minutes ago or 1 hour ago. And then for the other one is 1,000. Yes or no? So that's point C. It is 1,000 pound-inch. Remember that. We are going to continue with this next time, but I'm explaining to you what happened here now. First of all, there is not one shaft. This is 3-part shaft. Yes or no? So A to B, B to C, and C to D. Correct? Now, can you tell me what's the internal torque in AB? Internal torque in AB is 800. Yes or no? It's going this way. Yes. You can go all action. You can go all reaction. Doesn't matter. But since this is fixed, and this is going that way, so the rotation of AB is going to be clockwise or counterclockwise. That's what you were asking in a way. Is it clockwise or counterclockwise? It's going to be action-wise. It's going to be clockwise. So clockwise is negative. So if I'm looking at the phi of this point with respect to D, I have to look at internal. Now, the internal part, action-wise, here is, I'm going to put here, in color. The color means stress, not means actual. So I put it here, the TAB. TAB is not T at A or not T at B. TAB is here. Everybody understand that, but that will not be working, which is equal to 800, and it is 800. Let's assign a sign to it, as if it's going clockwise. Yes or no? I'm looking at all the action. Now, what problem is, don't go from action to reaction. Always keep action, 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 or reaction, 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 reaction. You will be fine. Don't jump around. Is that understood? Because they are equal and opposite. So then, when we go here, what is the internal torque there? It's not 2,400. I hope you are not saying that. 2,400 minus 800, so it is 1,600, but it's going on the opposite side. So it's counterclockwise, so therefore it's positive. So DBC equal to actually plus 2,400 minus 800. So it is 1,600 pound-inch, and it is like, is that correct or not? Yes? And the same. So this is, you see that this is a routine you have to follow, and you should not make any mistake, because I can change it from problem to problem to problem. Everybody understand that. TCD is how much? TCD now is equal to another 1,000 added in the counterclockwise, so it becomes 2,600. Yes or no? So it has become 1,000 plus, actually 3,400 minus 8,000, or 2,600, or 2,600 pound-inch, and this is also correct. No? Now, if these are all the same size, which one gets the highest stress? Now, let's think about it rather than work on it. This is very simple. If the shaft is all the same size from the beginning to the end, which side do you think, which part do you think they get maximum stress? CD. Is that correct or not? Because CD, tau equal to what? Tau max or this one, doesn't matter. We go with tau max. You got TC over J. T is different. J is the same. C is the same. Is this your problem at the same size or different size? Different size. Everybody see that? There are different length, different dimension too. So I don't know which one is best. So I have to check all the tau. Tau here is different size, different size. So J and C changes. So the first question is, what is tau max in this shaft? I don't know. Because torque changes, area changes too. Everybody understand that? So therefore, I have to check tau to see which one is maximum. Is that correct or not? For AB and BC and CD. Now the next question, which is really the toughest one, which is now you can know that. What is the angular of rotation of A with respect to D? Is that correct or not? So what should I do that? If I'm looking for, guys, angular rotation of the phi with respect to A with respect to D, because I'm assuming D is not moving, yes or no? Okay, you just showed me before. This one, AB is going how much? AB is going negative, like the delta, minus phi of B with respect to A. In other words, calculate phi of this one according to the second formula. Phi equal to TL divided by GJ, but it's going to go clockwise, therefore it is negative. But BC is going negative or it's going positive? BC is going positive. So in other words, like delta, if this was compression, this was tension, this was tension, this was plus, this was plus, this was minus. So you will adding and so here is the phi. What is the difference? So you have to add the phis together or subtract. So exactly the same concept. And this one, so you calculate phi of C with respect to B. So you have to put this tau, this T, L changes, G changes, J changes, everything may changes, or everything may be the same. Is that correct? And finally, phi of C with respect to D, because D is called the plus phi. So you have to use that formula 3 times, like delta minus delta 1, minus delta AB plus the. That's the same concept. Nothing changes. And by the way, if I tell you use a composite indeterminate, you have the idea. Next problem down there is in that you see that. The only thing that you don't know yet is the middle problem, which is the gear system. I'm going to talk about it. I'm going to do example 1, 2, 3, all of them in class. So you are covered everything. Everybody understands. So Tuesday, perhaps we are going to finish the whole chapter, because the whole chapter is the repeat. The only change is the formula. Everybody understand that? Yes? Okay, good luck and see you next. No, this is not about your next quiz. This is about the 2 weeks from now quiz.